Welcome back to Math 104. In terms of the normal curve, we have a region underneath the normal curve, and the area under the curve between this location and that location is pretty comparable to the area within the histogram painted in yellow. Now, what are these boundary points for our interval? In terms of the scale from 0 to 10, the lower bound is 5.5, and this upper bound is 8.5. Notice how the width of this interval from 5.5 to 8.5 is 3. And it should be 3. It makes sense when you look at the picture that the distance from the left boundary to the right boundary should be 3. The common mistake is to think that it runs from 6 to 8. But if you looked only from 6 to 8, you'd be missing part of the leftmost yellow rectangle, and you'd also be missing part of the rightmost yellow rectangle. You really have to look from 5.5 to 8.5. This is sometimes known as the continuity correction. Having made that adjustment to mark off the right region under our normal curve, we have to turn these into z-scores. Let's call the z-score corresponding to 5.5 z1, and let's call the z-score corresponding to 8.5 z2. z1 equals 5.5 minus 5 over 1.5811. That turns out to be approximately 0.32. And z2 equals 8.5 minus the mean, all divided by the standard deviation. And that turns out to be approximately 2.21. Now we go to the table. We look up z1 equals 0.32. That will tell us the probability of this region in here from the mean to 5.5. And that's 0.1255. There is a 0.1255 probability attached to this thin sliver between 5 and 5.5 along our horizontal axis. When we look up z2, which is 2.21 in the table, that tells us the probability of between 5 and 8.5. That whole region from the mean all the way up to 8.5 has a probability of 0.4864. So if we count everything from 5 up to 8.5, we have to throw out this sliver that we don't want that's still in blue, so that what we're left with is just the region in yellow here. We therefore subtract the 0.4864 from the mean to 8.5 minus the 0.1255 from 5 to 5.5. That difference equals 0.3609. While we're at it, let's go and visit this excellent website, which we've actually looked at before. If we type in area from 5.5 up to 8.5, with n equals 10 and p equals 0.5, those are exactly our parameters, those are exactly the right inputs. It will tell us that the selected area in yellow here is 36.62% of the total area. In other words, the probability of 6 or 7 or 8 heads in 10 flips of a fair coin is approximately 0.3662. What we just computed using our normal approximation was 0.3609. Again, not bad. But all that was really a warm-up. What we really care about is the culminating example of the course. We've seen examples like this, but now we'll see what's really going on. Suppose that 70% of people in New Jersey are in favor of reducing Rutgers tuition. A pollster who does not know that 70% is the true level of public support tries to find out what percentage of people in New Jersey support the reduction in tuition. How? By taking a survey of 100 people. First, recall what it means for a sample of 100 people to be exactly representative of the whole population. The histogram would look like this. We think of each individual person as a Bernoulli trial. The experiment here is to run 100 Bernoulli trials, 100 independent Bernoulli trials, where in each trial there is a 0.7 probability that the person supports the tuition reduction and a 0.3 probability that the person does not. For 100 people to be perfectly representative of the entire population, that would mean that exactly 70% of them, that is, 70 people, would say, yes, I do favor the tuition reduction, and exactly 30 people would say, no, I don't. We know how to compute the exact value of that probability. It is 100 choose 70 times 0.7 to the 70 times 0.3 to the 30. That's just the binomial probability model applied to 100 Bernoulli trials. where we hope for 70 so-called successes, each of which has a 0.7 probability, so that the probability of failure is 0.3. So 70 successes, 30 failures. That probability equals 0.0868. There is a less than 9% chance that if you survey 100 people, the 100 people you happen to ask will be exactly representative of the larger population. That's a pretty small chance. It is very unlikely that 100 randomly selected New Jersey residents will be perfectly representative of the entire New Jersey population on this issue. In practice, we therefore allow some margin of error. Our next task, then, is to approximate the probability that a sample of 100 people is accurate within a margin of error of plus or minus 4%. That means that the percent of population in favor of reducing tuition, according to the poll, is between 66% and 74%. If the pollster samples 100 people, and it turns out that only 66 of them are in favor, and therefore 34 opposed, that suggests that 66% of everybody is in favor of this tuition reduction. That would be wrong. It would be a low estimate, but it would be off by only 4%. If the pollster happens to survey 100 people, 74 of whom are in favor, and therefore 26 opposed, the pollster will think that 74% of the whole population is in favor. That will be an overestimate, but it will be off by only 4%. Anything between is still within this margin of error of plus or minus 4%. Here is the histogram with the range highlighted in yellow of outcomes that count towards the event that the margin of error is within plus or minus 4%. So first we want to approximate what is the probability that when you survey 100 people, the 100 people you find do fall within this range. In other words, they might not be exactly representative of the full population, but they're reasonably close. And then we want to say how much is a 4% error measured in people, and how much is a 4% error measured in sigmas, measured in measuring sticks, measured in standard deviations. The following is essentially the same histogram, but zoomed in more closely on an interval around 70. That just makes it easier to look at. Again, we see that the normal distribution is so closely clustered around its mean that very many of these outcomes far away from the mean are virtually impossible. They could happen, but they have tiny, tiny probabilities. We're not really losing anything by zooming in like this around 70. The probability that a sample of 100 people is accurate with a margin of error of plus or minus 4%, if we write it exactly, that is the probability of exactly 66 people, or exactly 67, or exactly 68, or etc., or exactly 73, or exactly 74 in favor. If the number of people in favor is anywhere from 66 through 74, then our event highlighted here in yellow is happening. When we write this out exactly, the binomial model tells us, here's the probability of 66 in favor. 100 choose 66, 0.7 to the 66, 0.3 to the 34. It's built into the experiment that the probability of somebody saying yes is 0.7, and the probability of someone saying no is 0.3, so this is 66 yeses and 34 no's. Or 67 yeses and 33 no's, etc., up to 73 yeses and 27 no's, or even 74 yeses and 26 no's. If you computed this whole sum, that would be a bit of a production, but it would give you the exact probability of this event. And to be honest, that website at Berkeley, if you type in the right numbers, will tell you this probability without any extra work on your part. But let's use our new method, which is quite powerful. Here we have a raw score of 65.5 people in favor. That's when we pretend that we're dealing with continuous data. And here we have a raw score of 74.5 people in favor. That actually makes sense. The distance between these is 9, and there are 9 rectangles painted yellow. Let us call 74.5 z standard deviations above the mean, and the lower limit has a z-score of negative z. To compute this z, we find 74.5 minus the mean divided by the standard deviation. The mean here is 70, so 100 times 0.7 is 70, and the standard deviation is found by plugging in n equals 100, p equals 0.7, and therefore 1 minus p equals 0.3. When we compute this, we have 4.5 divided by a standard deviation of a little bit more than 4.5, and that comes out to 0.98 standard deviations above the mean. When you look up 0.98 in the table, It tells you a probability of 0.3365. That refers to a region under the normal curve, not exactly the region shaded in yellow to the right of the mean, but it's close. That means we have another 0.3365 on the other side of the mean. Thus, the probability that a sample of 100 people is accurate with a margin of error of plus or minus 4% is approximately 0.3365 plus another 0.3365, which equals 0.6730. That makes sense. We found that our region is approximately one standard deviation on either side of the mean, a little bit less than that, and so the probability comes out to be a little bit less than 68%. That agrees with the numbers that we've seen a little bit earlier for falling within one standard deviation of the mean. Now, how much is a 4% error measured in people, and how much is a 4% error measured in sigmas? Well, in people, that's just 4 people, right? 70 plus or minus 4 people. And although we just computed 4.5 divided by the standard deviation, I'd like to see what we get when we find 4 people divided by the standard deviation. How many times does the measuring stick go into 4 people? 0.8729 measuring sticks go into 4 people. 4 is approximately 0.8729 copies of sigma. Why are we computing this? You'll see shortly. Now we want to see the effect of polling 400 people instead of 100 people. We continue to assume that 70% of the population is in fact in favor of the tuition reduction. So first, write an expression for the probability that the sample of 400 people is accurate within a margin of error of plus or minus 4%. Now we have to think, what's 4% of 400? That's going to tell us what the interval is on either side of the mean. We also have to think, what's the mean going to be? Now the mean is going to be n times p, which is 400 times 0.7, and that's 280 people. If a sample of 400 people should just happen to be exactly representative of the larger population, then that perfect sample of 400 people would have exactly 280 who say yes, I'm in favor, and another 120 who say no, I'm opposed. So that's going to be our mean. That's going to be right in the middle. How much is 4% of 400 people? That's 16 people. So our range here, measured in people, is 280 minus 16 up to 280 plus 16. That means 264 or 265 or 266, etc., all the way up to 295 or 296 in favor. Any number of people in favor of the tuition reduction, ranging from 264 in favor, that's exactly undercounting by 4%, all the way up to 296 in favor. That would be a sample that has 4% too many people saying yes, I'm in favor. Any sample with the number of people in favor of the tuition reduction within this range counts towards our event. Any such sample is reasonably close to representative of the true population, with a margin of error of plus or minus 4%. When we roll up our sleeves and apply the binomial probability model, we have probabilities ranging from 400 choose 264, 0.7 to the 264, 0.3 to the 136. The 0.7 and the 0.3 are still the same, because the underlying Bernoulli trial is still the same. We're just performing 400 of them instead of 100. These exponents better add up to 400, but the 0.7 is raised to the number of yeses, and the 0.3 is raised to the number of noes. That corresponds to 264 in favor. Then we have plus the probability of exactly 265 in favor, etc., all the way up to plus the probability of 295 in favor, plus the probability of exactly 296 in favor. If we didn't have a nice web page that with a few keystrokes would compute this for us, this would be a painful amount of work sitting there with a calculator computing each application of the binomial model. Before going on to the next video, answer the following questions. Use the normal approximation to the binomial model to find a good approximation to the probability that the sample of 400 people is accurate, with a margin of error of plus or minus 4%. And then, how much is a 4% error measured in people? We actually already found that. And how much is a 4% error measured in sigmas?